This is part 2 of the combined power, heating, and cooling feasibility analysis with the RETScreen Expert software. In this video, we will go through the energy analysis sheet with more details using a combined inlet power example. We will also vary some of the key parameters to show the impact on the financial viability of the project. Before starting this demo, we have downloaded a built-in example using the Virtual Energy Analyzer. It is a combined heat and power system for an apartment building located in Toronto. The energy model sheet looks pretty simple, but when you start clicking on the various components, you will discover that it contains a lot of information. The best approach is always to either follow the steps in the ribbon or to go through the left menu from top to bottom. In step 1, system selection, because the type of system has already been selected in the facility sheet or in the VEA, the user could simply validate that information. The components included in the left menu and the top ribbon also depend on that selection. A simple schematic of the type of system selected is also shown for consultation. You may recognize here from that schematic the basic of the cogeneration system. If you, for example, decide to add cooling to your combined system, you could see the cooling section being added to the ribbon, the left menu, and the schematic. If you move to the facility sheet, you will as well notify that the type selected was modified accordingly. The grid type will allow you to specify if your facility has access to a center grid or an isolated grid, or if you are simply not connected to a grid in an off-grid scenario. An isolated grid means that yes, there is a grid available, but the capacity of the grid to provide and receive electricity is limited, which means that some additional verification needs to be done to find out if the electricity can be exported to the grid by the proposed case power system. This will be done in RETScreen by showing warning icons. In the electricity and fuel section, the VEA has proposed a rate of 30 cents per cubic meter for the natural gas. Some may think that this value is on the high side and may want to modify the value. This could be done directly by typing the new value. Alternatively, the user could modify this value into the Settings section of the File tab. This will set the rate to its new value whenever the VEA is ran. 3 rates have been proposed into the electricity section. The VEA proposed a rate of 10 cents per kilowatt hour for all 3. In many cogeneration applications, the rate that the utility is charging for the electricity consumed after the installation of the CHP system will be higher than what it used to be. An agreement has to be negotiated with the utility regarding the electricity export rate. We are going to keep those costs unchanged for now, but we will return and change them later during the demo. In step 2, the heating load for the apartment building is being estimated. Since we are looking at only one facility, single building have been selected. However, if the building could be separated into more than one zone and a different load could be associated with each of them, the multiple zone option could be selected. In the same way, if the system consists of multiple buildings in a district energy scenario, multiple buildings could be selected. The load type could consist of space heating only, but process heating could also be considered. The user could select both types or only one of them by clicking on the icons. The form layout will depend on those 2 selections. In single building and space heating load-only situation, the user will start first by entering the heated floor area for the building. This value is set to 45,000 square meters. A unit switch could help convert or enter this value in an alternative unit. The fuel type is selected. The list of fuels will be based on the fuel selection done in step 1. The efficiency of the heating system is entered. Be aware that the model is looking for the seasonal efficiency and not the peak load efficiency. The heating load of the building in watt per square meter is then entered. To evaluate this value, the VEA uses the building heating load chart available in the online manual. The design temperature was read from the climate database in the location sheet, and the assumed building insulation was medium. Since this curve is known to be useful for residential more than other applications, we may have modified the curve for some of our VEA archetypes, for instance, the hospital. By using the information from that form and the climate database, the model will estimate the peak load in kilowatt and the heating energy in megawatt hour. The detailed methodology used to perform these energy calculations are explained in the section 2 of the RETScreen e-textbook. Based on the calculation above, the model is also calculating the fuel consumption for the base case heating system. Because this value may be known by the user from utility bills, an iterative method could be used to adjust the heating load of the building derived from the curve until a reasonable match with the utility bill is obtained. Finally, the user could enter in the next cell the percent of the base case heating system peak heating load that is reduced as a result of implementing proposed case and use energy efficiency measures. We are going to assume here that we would reduce by 10% the heating load. The cost of the measure would be around $100,000. In the power load and load characteristics, in the base case section, the utility bill could be used to enter the power gross average load on a monthly basis. A percentage could be used to evaluate the annual peak power load. If electricity is not used to provide heating or cooling in the base case scenario, the power net average load is going to be equal to the gross power. The monthly heating average load will also be derived from the heating load section above. In the bottom section, the proposed case power net average load will be calculated taking into account the potential and use energy efficiency measure that could be implemented prior to the installation of the cogeneration system. In this case, we will propose an investment of $100,000 to reduce the load by 10%. The proposed case heating net average load is also displayed. The proposed case load and energy table on the very bottom of that page simply summarizes the result and could be used in the next section when sizing the equipment becomes important. The load characteristic graphs could also be consulted. Note that the options section of the ribbon gives you the opportunity to see those graphs next to each other when choosing the landscape display. Now that the loads are well defined, we are ready for step 3, which is the equipment selection for the proposed case, our cogeneration system. By clicking on Power Equipment, the user could select from the available technologies for the base load and intermediate load power system. In this case, a gas turbine is selected for the base load. No intermediate load is selected for now. The gas turbine form begins with the fuel selection. In this case, natural gas is selected and the cost of the fuel is shadowed. The power capacity of the gas turbine is set to 200 kilowatt. One of my design criteria may have been to select a power system that represents 50% of my peak power load. Since this value is 519 kilowatt, I could specify a power capacity of 250 kilowatt to use a round number. I am curious to find out if the product database contains such a product. In the product database, gas turbine have been already selected for me. I will confirm that I am not considering a combined cycle unit by selecting gas turbine in the cell below. Since our database contains a wide range of products, I will limit the capacity range to 100 to 300 kilowatt. I found in the database a turbine that has the exact capacity that I am looking for. If I observe the heat rate that is given for that particular unit, I could see that a low heating value of more than 11,000 kJ per kilowatt hour is specified for this unit. Since the software has been set to use high heating value, I do not want to change the setting. I am going to estimate my HHV using a rule of thumb. That is multiplying my LHV by 1.11. Then I am going to paste the information from the product database and immediately change the heat rate from 12,000 to 12,600. I will keep the minimum capacity to 40%, the availability to 95%, and the heat recovery efficiency to 60% as suggested by the VEA. The cost database contains, for now, the cost of the installed power plant system and not the cost of the complete cogeneration system. It does not include, for instance, the cost of the heat recovery system. I will trust the costs that have been suggested by the VEA and keep the cost unchanged. Note that we are presently using the version 7 of RETScreen. The cogeneration cost database will be added to the software in the next version. The outputs of the calculation in the gas turbine section includes the heating capacity, the fuel consumption, the electricity delivered to the load, and the electricity exported to the grid. The operating strategy section will allow the user to select between three options: full power capacity output, power load following, and heating load following. In the second option, because the system operates to always follow the power load of the building, there is no possibility to export power to the grid. In the third option, we should always expect a higher efficiency. The operating profit column is highly dependent of the various rate entered previously for the fuel and electricity. In this case, we will select the scenario that is the most profitable: full power capacity output. Into the system characteristics section, the user could first select the remaining components that have not been selected in the above section: the peak load power system, the intermediate and the peak load heating system. A system capacity is suggested in order to make sure that the peak load for every system is met at 100%. If the load is not met, a warning message is going to appear. If the seasonal efficiency is forgotten, again, a warning message is going to notify the user. In some cases, when the cost of the new equipment could be avoided by recovering the existing equipment, the costs of those are not needed to be entered. The system design graph could help you understand better the proposed system. For instance, if we observe the system design graph for the power project, even though the system has a capacity that represents 50% of the peak heating load, it is providing more than 80% of the required power energy on an annual basis. The heat recovered from the gas turbine power generator is going to provide about 36% of the heating energy. These graphs, along with the system summary section, are summarizing very well the result of this analysis. Let's now look at the financial viability of our project. In part 1 of this series of video, we have verified that this project had a very poor financial viability. By reviewing carefully the data entries and by making sure that energy efficiency measures are considered upfront, before the implementation of the cogeneration system, we were able to improve the financial viability of the project. The net present value is now positive. The simple payback is 11 years, and the IRR is greater than the discount rate, just over 9%. Let's review the cost of fuels as promised. These costs have been identified as the key components in the risk analysis tornado graph. They are the parameters that have the most impact on the financial viability of the project. As mentioned earlier, the natural gas costs for the region of Toronto may have been overestimated. We are going to propose a slightly lower number, 27 cents per square meter. The rate of the electricity will be adjusted to 13 cents for the proposed case and 12 cents for the base case and electricity export rate. We can now observe that the financial viability of the project is improved. In some cases, the utility may be interested in replacing the electricity export rate by an avoided cost of capacity. In this situation, the utility is willing to offer you a rate for the guaranteed capacity of the cogeneration system has to offer. In this case, the cogeneration is running at a full capacity, with a capacity of 250 kilowatt. The avoided cost of capacity calculated by the utility could be, for instance, $225 per kilowatt. We are going to apply the rate for the period of 20 years and an escalation rate of 2%. The electricity exported to grid could be set to 0. This shows that this incentive could also be an interesting option. Let's now look at the emission results. The emission factor used for the baseline electricity system was set by using the most recent published value from the province of Ontario grid electricity generation. Some may argue that this value should not be the current value of the grid, but should be the emission factor of any new power generation system installed in Ontario if the capacity has to be increased. It is more likely that any new installation will be a natural gas power plant. By using the Level 2 analysis, the user could set the baseline power system to natural gas and visualize the result. Let's not forget to include the T&D losses. Based on this last assumption, the proposed system is now reducing greenhouse gas emissions. Into the next presentation, we will add a cooling system to this analysis. We will also consider adding an intermediate power system and propose a cleaner fuel.